Hi, and welcome to the Machine Learning and Data Science track. For the talks today, if you can just drop your questions in the Q&A tab and vote on them, we'll take the questions at the end of the talk and give them to the presenter then. First up today, we have Sean Law, who will be presenting on STUMPY for modern time series analysis. Sean.
Thank you so much. So hopefully everybody can see my screen now. I'm really excited to be here today to tell you about modern time series analysis with STUMPY. I'm Sean. You can follow me on Twitter at SeanMyLaw. You can also follow the development of STUMPY on Twitter as well at Stumpy_dev. First and foremost, I'd like to acknowledge some folks. I'd like to say thank you to all of the organizers and session chairs, as well as all the volunteers at SciPy for making this wonderful conference and keeping it going. Also like to thank my employer, Charles Schwab. It's a finance firm that I currently work at. And at Charles Schwab, I am a principal data scientist working on a research and development team. But prior to this, I was in academia, so I was a postdoc doing molecular dynamic simulations. So I deal a lot with time series data in my past. And so let's get started, right? So what's the problem that we're trying to solve, especially in talking about STUMPY and modern time series analysis? So here's the problem. I'm sure we've all been there where maybe you generated some data, or your boss or some business partner or manager handed you some data and said, here's some time series data. Now perform some magic, Dr. McFancypants. All right, you've got an advanced degree. You should be able to impress me somehow. Now, if you're lucky and the data set is small, time series data is small, you might have 10 data points, and you can see that there's an increasing trend in the data, and you can visualize your data, and that's often sufficient. But what if your time series had 100 data points, right? And you can still visualize it. You can see that it goes up and it comes back down. Maybe you can look at some summary statistics, some global maxes and mins, some moving averages. That's fine too. Once you get to about 1,000 data points, maybe this is just over 3 years worth of daily data that you're collecting. Now what you're seeing here is that not only do you get trends, but you might get some seasonality where you're going up and down, up and down. But visualization still works pretty well in these particular cases. But once you get to about 1,000 data points, remember, this is perhaps new data that you've never seen before. Can you spot anything interesting from this data set? And I really, really want you to keep this picture in mind, because at the end, during the live demo, we're going to use this exact example to help drive home the point here. Now, I don't know about you, but when I move my eyes from the left to the right, I've already forgotten what I've looked at in the first place. Now, this is pretty complicated, and maybe there are interesting patterns here. Maybe there is not. Maybe I've added a line connecting all the dots just to trick your eyes, right? But hopefully there's some way for us to analyze this data to extract out important insights. But usually when I look at data sets of this size or larger, I just kind of get this overwhelming sense of dread. And oftentimes I just wish that there was some sort of magic spell or some magic wand that I can wave around so I can wish it all away. And perhaps that one of these magic spells that people typically use when historically, right, when dealing with time series data is that, again, they might visualize the data, but we've already talked about how above 10,000 data points, it's not so effective anymore. You can also reach for our good friend statistics. You can, again, compute these global maxes and global mins. But usually with time series data, very, very rarely are you interested in these single point statistics, because very quickly those points become uninteresting. But instead, what you're interested in is maybe parts or sections of your time series, right? And looking at the shape of continuous number of data points. Another very common tool in time series analysis is ARIMA, where you're building auto-regressive models. But oftentimes this makes it a key assumption, right, that something does repeat itself, right, that there's a pattern that does repeat. And that may or may not always be the case. And if you're pretty adventurous, you might reach for thinking about like anomaly detection. Are there anomalies within your time series? But now you have another issue, which is defining what does normal look like first. Once you've defined normal, then you can begin to start asking, well, what does abnormal or an anomaly look like? And then the next step is, if you've seen the anomaly once, that's fine. But what happens if you see it twice, or 3 times, or 4 times? Are those still considered anomalous? And then another thing that's very popular these days is looking at forecasting using tools like Facebook Prophet. But if you can imagine, forecasting requires good, solid historical data. And considering the fact that we're still in a pandemic right now, the last year's worth of data is probably useless for forecasting the future. Obviously, we could also do machine learning, building some machine learning models to predict some parts of maybe a future time series. But therein lies another issue where you might not be able to interpret your models easily. Really, with time series data, or any type of data, you want the ability to interpret these models, right? Or interpret the insights that are derived from them. Another thing that people might do is think about time series clustering. Given that you have many, many different independent time series, how might you group some of those time series together? But again, with clustering, this is an unsupervised method. There might not be a good way to benchmark whether or not these clusters are correct or not. And then another common tool is looking at dynamic time warping. Given that you have time series of different lengths, how do you compare them? So using DTW, you can shrink or expand them, right, just so you can match them up. But all these tools, most of these tools are approximate, right? They don't really give you an exact answer. And that's another issue too. And of course, in the day of artificial intelligence and deep learning, right, everybody's sort of favorite hammer looking for a nail to hit, right? But now that with deep learning, not only do you need a lot of time series data, but you need a lot of computing power, and you also have to build models that have sometimes millions, if not billions, of parameters to tune. And of course, the goal here isn't to point out all the pros and cons of all these methods, but it's really to identify that with any sort of data analysis method, especially if you're looking at exploratory data analysis, there's no silver bullet or there's no free lunch. Everything comes with some sort of compromise. Every tool that you reach for comes with some sort of compromise, right? Each tool is good for different things. So how might we approach this problem, right, to give us a more precise answer or precise insights? And so let's start off with an illustrative example, sort of to orient ourselves. So let's take this time series here. This is a time series with length n equals 13, so it has 13 data points. And if you were to look at it, you might see that, okay, it's bounded between 0 and the maximum is 15. Do you see anything interesting here? Are there any patterns or sections of this time series that sort of repeats itself? In fact, we can plot these data points. We can visualize it, as we mentioned before. Do you see anything interesting? And we're going to come back to this and use this as our motivating example. So maybe the first thing that we want to do when dealing with time series, right, is provide a definition. So the first definition is a subsequence. And you're going to hear me use this word time and time again, a subsequence. So a subsequence is a part or section of the full time series. So going back to our illustrative example, this could be a subsequence. It's a small part of length 2 of our full time series. This could be a subsequence. This is a subsequence of length 8. So all these are considered subsequences, as long as you're a part or section of the full time series. So now that we have this definition, and now that we sort of see, okay, we have a time series data, so then what's the goal? When we want to analyze time series data, what's really the initial goal, right? And I would argue that the goal of time series data, of analyzing time series, is this. If a behavior is conserved, there must have been a reason why it was conserved, and then teasing out these reasons or causes is often very, very useful. And when we talk about conserved behavior, we're talking about potential patterns, okay, or repetition of contiguous data points. And realistically, we can ask two key questions whenever we are presented with any time series data. The number one question is, do any conserved behaviors exist in my time series data? So we don't make the assumption up front that a pattern must exist. We should ask the question, do any conserved behaviors exist? And then if there are conserved behaviors, where are they in our time series? And what are they, right? And whatever tool that we come up with should help us answer these two key questions. And this will really help us simplify the process of analyzing any time series data in general. And so as a reformed scientist myself, I like to focus on using Occam's razor, which simply states that simpler solutions are more likely to be correct than complex ones. So many of the methods that I mentioned before can be quite complex, right? And so what's a good approach that we can take? So what's a simple and intuitive approach that we can take? And whatever that approach is, whatever that method is, needs to be easy to interpret. That means that if I come back to that analysis or the results of that analysis, 3 months later, I don't have to perform any mental gymnastics in order to reorient my brain. I should be able to get right back into it within minutes, if not seconds. Another thing is that the approach that we take must be user and data agnostic. That means that it can be generally applicable to any data set, right? But also that it doesn't require expertise to use this capability. right? Or use this analysis method. And also, another key quality is for this approach to not require any prior knowledge. And sometimes what I mean by prior knowledge in this case, right, is that even prior human knowledge, but also doesn't require prior data knowledge, right? So if you think about building machine learning models, you're basically training on prior knowledge in order to build a model. But really, we want to be able to just take our data, analyze it, and get information out without any past information. And the last but not least is whatever method that we choose, hopefully it's parameter free. Or if you had to choose a set of parameters, it'd be as little parameters as possible. And in the choice of those parameters, they must be intuitive and obvious, right? It shouldn't be just some esoteric type quantity that we're choosing. And so if we're thinking about time series, again, one of the key parameters that we can choose is the subsequence length, m. Right. So in this particular case, this is a subsequence of length 4, so m is equal to 4. Very simple. Now that we've defined what a subsequence length is, then we can start asking, how might we start comparing subsequences? Because ultimately the goal is to find patterns within our time series. So how might we compare, let's say, this light blue subsequence with this dark blue one all the way on the right here? Now, the most simple and intuitive way that I know to compare subsequences is to compute something called a Euclidean distance. And this is just simply the straight line distance between any 2 points. So going back to our example here, maybe we don't start with subsequences of length 4. Let's simplify this and start with subsequences that are a bit shorter, so of length 2. So we have the light blue one, we'll call that x, and it has 2 data points in that subsequence, that's x1 and x2. And similarly, the darker blue one is y, and has y1 and y2. We can actually just plot these subsequences, right? So the blue one down at the bottom, y is up at the top, and the Euclidean distance is simply the straight line distance between them. And maybe to simplify, we won't use all this jargon, we'll just call it h, and that's the distance between them. And in fact, most of you actually know how to compute this distance between them. And we do this by simply drawing a right angle triangle, labeling the sides of them, and we can see that the distance between these 2 subsequences can be computed from h squared is equal to a squared plus b squared. And hopefully this is pretty familiar to all of you, and this is nothing but Pythagorean theorem. Now, how does this translate into longer and longer subsequences, right? Sorry, before we do that, let's plug in our values into our Pythagorean theorem, and we get that the distance between these 2 data points is square root of 2. Now we can extend this to subsequences of length 4, right? And what you'll notice here is that we have now an x3 and y3 term, and we update our Pythagorean theorem with a c squared term. Similarly, for the x4 and y4 terms, we add an additional d squared term. And as your subsequences increase in length with 5 terms, 6 terms, and so on and so forth, you'll have an e squared term and an f squared term, right? And so we have a method here that allows us to scale up to any length subsequences. So we can compare any length subsequences. So going back to this example here, we can actually now compare these 2 subsequences. We plug in our values, and we get that the distance between them is square root of 67, right? Now, in this particular case, you're given 2 subsequences to compare. But in fact, what if I want to go back to our original question, which is this subsequence here, this light blue one, conserved, right? Or does it repeat itself anywhere along this time series? To answer this question, what we can do is we can repeat our time series, right? And we can actually take a dark blue box and compare the light blue to the dark blue. And we can store that Euclidean distance down in a distance vector down at the bottom. So if I compare the light blue and the dark blue, they're exactly the same. And when we compute the Euclidean distance, this distance is 0. Now then what I can do is I can slide over that dark blue box over by 1. And I compare them again. And I compute the distance. And I keep doing this, right, until I get all the way to the very end. And I've compared the light blue subsequence with every single subsequence along the time series. And this is what is referred to as a distance profile or a distance vector. This tells you full information, right, of every single subsequence along the time series relative to the light blue one. Now, what's interesting here is that we can then say, okay, is this subsequence, is the light blue subsequence conserved? And we look for the smallest number. In this case, this dark blue one matches the light blue one. Well, of course, this is what is often referred to as the trivial match or the self-match. And it's not particularly interesting, right? So we often ignore that one. And then the next thing that we do is we scan along the remainder of our distance profile and look for the next smallest number. And that's this one right here, right? This dark blue subsequence is the closest one, the absolute closest one to the light blue subsequence. And it has a distance of 6.9 away. Nothing else is closer, right? And now we can actually repeat this not only for this single light blue subsequence, but what we can do is we can slide that light blue subsequence across as well and compare all possible subsequences with all other subsequences along the time series, right? Computing all of these distance profiles along the way. And if we stack these distance profiles together, remove the unimportant parts, then what we end up with is a pairwise distance matrix. All right. And with this distance matrix, this is an exact computation. It tells you all the information that you would probably ever want to know about conserved behavior or patterns within your time series data, right? Because you can get to compare subsequences with everything else. And if you were to ask me what's the most simple and intuitive approach, I'd say that computing this distance matrix and interpreting it is pretty easy. It's user and data agnostic. You can apply to any data, and it doesn't require training any fancy machine learning models behind the scenes. And the only parameter that we've chosen is the subsequence length m, right? So far, it's pretty simple and intuitive. But wait, there's got to be a catch, right? Because just because it's simple and intuitive, we should really be asking ourselves a second question, which is this solution scalable to compute this distance matrix? So since we're at a Python conference, let's write some Python code to actually see what it takes to compute this distance matrix. So we'll start off with our time series, TS, right? And these are our original 13 data points here. N is the length of our time series, and the length is 13. And then M is our subsequence length. To compute this distance matrix, it just requires 6 lines of Python code. Now, I'll draw your attention to the fact that there are 3 nested for loops. So the for I loop controls the sliding of that light blue subsequence. The for j loop controls the sliding of the dark blue subsequence. And that for k loop controls the computation of the Euclidean distance, right? So the a squared, b squared, c squared, d squared terms, and so on, right? And it turns out that to compute the distance matrix for any length time series, it requires O of n squared by m time, computational complexity time. And furthermore, because it's we have this distance matrix, it requires O of n squared memory. What does this mean practically, though? So if we imagine some sort of, using an example here, right? This is a back of the envelope brute force calculation. Imagine that we had a thermostat in your home, right, or in your office that's collecting data, right? A sensor reading, right, of the temperature for 5 years straight, 365 days a year, 24 hours a day, 60 minutes every hour, 20 times a minute. That means that for 5 years straight, every 3 seconds, you record the temperature. This amounts to just over 52 million data points. And if we were to use this brute force method to compute this distance matrix, it turns out that it would take you just over 4.4 years to compute the full distance matrix, the exact distance matrix, and over 11 petabytes of memory to store that information. And so if you were to ask me, is this solution scalable of computing this full distance matrix? Sadly, it's not. And it kind of explains why all of these, magic spells or these classical methods have gained so much attention and so much use over the decades. And that's also why, even though the distance matrix is so interpretable, it has fallen out of favor, except for very small toy data sets, even though it provides an exact solution to understanding your data. That is until now. So back in 2016, a group of researchers over at the University of California, Riverside, as well as the University of New Mexico, published a series of back-to-back papers detailing a data structure called a matrix profile, along with some very, very interesting algorithms. And so what is a matrix profile? They define the matrix profile as a vector that stores the distance between each subsequence within a time series and its nearest neighbor, and its one nearest neighbor. Believe it or not, you actually know what this means. So if I show you the original distance matrix, the one nearest neighbor is exactly where these light blue boxes are, right? So your nearest neighbor for every subsequence is shown here. And the matrix profile is nothing but extracting out that one nearest neighbor and storing it as a vector or as a profile. And that's the matrix profile. So you only care about the one nearest neighbor. And the good thing about this, about using a matrix profile, right, is that the space requirement or the memory requirement is now drops down to O of n, space complexity. But these researchers claim to be able to compute this matrix profile much faster in O of n squared time. And by virtue of having a matrix profile, they claim that you can answer these two key questions that we posed earlier. Do any conserved behaviors exist in my time series? And if there are conserved behaviors, what are they and where are they? So going back to our illustrative example, this is our original time series, and we can actually take the matrix profile for this time series, and we can annotate our original time series. So notice here that the matrix profile is aligned specifically with the start of each subsequence, and we can actually plot that matrix profile as well. Okay, and so how do we interpret this matrix profile? So for the first subsequence, what this matrix profile is telling you is that its nearest neighbor, its one closest nearest neighbor, has a Euclidean distance of 6.9 away. Or maybe this subsequence over here, its nearest neighbor has a distance of 1.4 away. Or the one all the way at the very end, its nearest neighbor has a distance of 6.2 away, but nothing else is closer. Okay. Now, how might we leverage this matrix profile to answer that question of, do any conserved behaviors exist? So to answer that question, all we have to do is look along our matrix profile and identify the minima. So we can visually see that in our matrix profile, there are two global minima. There's one over here and one over here. And that corresponds to these two distances. And the one on the left corresponds to this subsequence. The one on the right corresponds to that subsequence. And there, in this entire time series, there's no other subsequences of length 4 that look closer to each other than these two. So you see the first two numbers are both 1 and 1, identical. The next two numbers are 3 and 2, to just 1 off. The third numbers are both 2. The last number is 9 and 10, just off by 1. Now, if both of these subsequences were identical, the distance between them would be 0. But because there are some slight differences, the distance between them is 1.4. And so this is a potential pattern, right, within your time series. And oftentimes in time series analysis, this is referred to as a motif. So it's a potential pattern for you to go and explore further. So you now have a tool. Once you complete the matrix profile, you have a tool that will tell you where should you look first in your time series data. Now, there is a second definition here from these papers, which is a matrix profile index. This index is the index location of the nearest neighbor for a given subsequence. So I'll draw your attention to the very top. I have a zero-based indexing, right, to allow us to index a complementary subsequence. And so for the light blue subsequence on the left, its nearest neighbor is a distance of 1.4 away, and it's located, the nearest neighbor is located starting at index 8. And similarly, for the subsequence on the right, the dark blue one, its nearest neighbor is located starting at index 1. And in fact, for every single subsequence along this time series, not only do you have a nearest neighbor, but you can also find where the location of the nearest neighbor is starting at. Okay, and that's how you interpret this data structure. Also, maybe just to practice here, let's say for this subsequence, if we look at our matrix profile and matrix profile index, we just scan straight down. We see that the nearest neighbor to this subsequence is 6.2 away, and it's located over at index 2, which corresponds to this subsequence. Okay, great. So we mentioned that the brute force way is pretty slow, and that's why nobody ever used it in history until now. And these academic researchers published their first paper, and they introduced something called STUMP. That's the algorithm for computing a matrix profile, leveraging fast Fourier transforms. But they later published a second paper detailing an algorithm called STUMP that uses some very nice math and algebra and a look-ahead sort of method that reduces this computational time down to O of n squared. And then they ported this algorithm over to GPUs. So if you have access to GPUs, that's great. And they can also further speed the computation up. And they actually took a data set with over 100 million data points. This is more than double. This is about double the back of the envelope thermostat example that I gave. And they were able to use their GPU STUMP algorithm and computed the full matrix profile in just over 12 days. Now, mind you, the brute force naive implementation would have taken just over 1,500 years to compute all of these pairwise distances. Remember, this is exact, right? There's not an approximation here. There's no cutting corners. And in fact, if you might think that 12 days might seem slow for 100 million data points, but it would have taken you 10 years to accumulate that data set, right? For obviously much smaller data sets or for streaming data sets, the speed is even way faster than this. And this is Lee-Monk Yeo. He's one of the original authors, and he said that given the matrix, that you can compute the matrix profile, most time series data mining problems are trivial or easy to solve in just a few lines of code. And in fact, these are some of the best ideas in time series data mining in the last 2 decades, right? And anybody who says that, to me, has to be a real gangster. And of course, extraordinary claims requires extraordinary evidence, right? And that's where STUMPY came into play. STUMPY is a powerful and scalable open source Python library that officially computes the matrix profile for you, and it can be used for a variety of time series data mining tasks. We have over 350 downloads and installs in the past 2 years since we started, and over 1,800 GitHub stars. And you can conda and pip install it. And most importantly, we have 100% code coverage, and we published in the Journal of Open Source Software. STUMPY has minimal dependencies. If you already have NumPy and SciPy installed, the only other additional dependency is Numba. And you can actually parallelize this using Dask as well. But Dask is not a requirement. STUMPY is very, very fast compared to even the GPU STUMP implementation. We also computed the matrix profile using 256 CPUs, so it's very scalable. And we computed that in just under 10 days. We call our implementation of this matrix profile calculation STUMP, or STUMPed for the distributed Dask version. We also have a GPU, a very, very fast GPU implementation. And so if you ask us what's the most simple intuitive approach, and is this solution scalable? Yes, it definitely is. And so to use STUMPY, you just have to provide your time series data. So this is an example. And you need to call STUMPY by saying stumpy.stump. You pass in your time series, you give it your subsequence length, and then that's it. You compute your matrix profile. And to use the GPU version, it just requires 4 additional characters. And so we also support multidimensional STUMP, as well as Scrump, which gives you an approximate matrix profile, as well as STUMPY for incremental analyses as well, if you have streaming data. And just so you know, this is only the tip of the iceberg. And there's a lot of stuff that can happen under the hood that you can leverage the matrix profile for, including time series chains, semantic segmentation, which is related to change port detection, also for computing machine learning features, and much, much more. Why should you use STUMPY? Well, again, it's user-friendly, developed for scientists as well as data scientists and engineers. It's highly interpretable, given that it computes a Euclidean distance. It's fast and scalable, supported both multi-CPU and GPU support, as well as 100% code coverage, always. So it's very, very reliable and complementary, right? So you should mix and match using STUMPY with any of these classical methods, right? Hopefully you have a new tool in your tool belt that you can use at any time, but that is fast and scalable. Because remember, there's no silver bullet here. So I'm going to switch to a live demo before I quickly move to questions, if there's time for that. So given this time series that up at the very top here, this was the same time series that you saw before. Do you spot any patterns, anything obvious? And not to belabor the point, even if I showed you, I cheated and I showed you that this is the pattern that you're looking for, right? Oh, just refresh here. Even if I showed you that this is the pattern that you're looking for, can you spot it? And not to belabor the point, but the pattern that matches this is all the way on the far right. So I've superimposed these 2 patterns here. Then you can see that they're a pretty close match. And if for the astute observer, you'll see that this is the matrix profile down below here. And the minima is exactly where the 2 patterns are located. And in fact, what STUMPY doesn't only give you the closest match for a single subsequence, it gives you matches for every single subsequence along your time series. So you notice that your time series might have a match that is before or after as well. So I recommend that people play around with STUMPY and also check out our documentation. We have great tutorials that come with binder, interactive binder sessions as well. So I recommend that everybody check it out. And so with that, I know I'm running short on time. I'm going to leave this slide up here for everybody to see. And I welcome any questions. And also, I'm going to hop into one of the lounges in AirMeet right after this. So if you have any questions, please come and join me and share your questions there. And thank you very much for your time.
Thanks so much, Sean. We have a little bit of time for a couple of questions. First one, somebody would like to know the name of the article that discusses matrix profile. So if you could, if you have that on hand, that would be great.
Yeah, actually, what I recommend then, right, is if you go to our tutorials, so it's tiny.cc, stumpy-tutorials, and when you click on each tutorial, at the bottom of it and throughout the tutorials themselves are direct references back to the original published work.
Another question, you mentioned that the matrix profile is a good place to figure out where to start looking. So what kinds of questions do you typically ask next in your workflow?
Yeah, again, beyond the scope of the session here, but again, the tutorials will give you a lot of different examples of things that you can look at. Another thing that you can look at, given the matrix profile, right, is identifying potential anomalies as well. So not only are you looking at the global minima, but you can also look at the global maximum as well. In addition to that, I had mentioned looking at repetition of patterns, right? Sometimes you might have a pattern that you already have in hand, which makes the problem easier. Then you can take that pattern and then ask, right, does this single pattern repeat itself? Where in that data set? Again, we have tutorials for that as well. You can also compare two different time series, right, and finding patterns across two different time series or across multiple time series. So those are all possible things that one should look at, right, to focus your attention on interesting insights in your time series.
All right, thank you so much. Let's thank Sean again. We're out of time, but please find him in the lounge. There were lots more questions in the Q&A, so you can find Sean in the lounge and ask all your questions there. Thank you very much.
Thank you so much.